Hello there, welcome in the lecture of the topic mechanical properties of solids. In this video we are discussing the basic concept of mechanical properties of solids, and in the second part of this topic we will discuss some hyperphysics related to the terms which are belong to the mechanical properties of solids. Okay, so in this video we are taking just general idea of the terms which are necessary to understand the phenomena related to the elasticity and plasticity and the behavior of the substances according to their elasticity and plasticity. Okay, so here our topic is mechanical properties of solids, and this is the part 1 of this lecture. Okay, so let's start to know about the terms which are related to this topic. Okay, one thing you should know in the physics that if you want to categorize the substances of the universe which are available there, you have to take some base. Okay, for example, if you divide the substances according to their state, then they may be categorized into 3 general states, as you know: solid, liquid and gas. If you come across the forward states of the matter, then that are also BEC, Bose-Einstein condensate, and there is also that is known as plasma. So here we are taking the base to categorize the substances as matter or state. So matter can be categorized into the 5 states according to their state. First one is solid, another one is liquid, and the rest is gas, and another is BEC, and the last one, 5th one, is the plasma. So if you want to categorize the substances in the physics or on the science phenomena, on the science world, then you have to take some base, then according to which you are categorizing and you are dividing the substances into the different categories. Okay, so in order to categorize a substance by checking their mechanical properties, we are taking the base of the solids as their elasticity. The term elasticity, you know very well, it is just familiar word to the real world, the elasticity. This is the substance elastic and this is not elastic. So we are taking the elastic base of the substances. So it is very simple to understand that the solids in the natures, all the solids in the natures are categorized into 2 kinds. One is the elastic bodies, okay, and another is plastic body. Okay, these 2 terms are very familiar terms when we come across to the real life phenomena. Okay, so the first one is elastic substance and another is plastic substance. And what are the criterias which may possess by a substance, which can be possessed by a substance in order to say that this is elastic and this is plastic? Okay, so what you have to do, you have to apply some force on a particular body and you have to check the shape and size of the body when you are forcing the body by some linear force. Okay, so we are taking here a body. Let's say this is a body which are placing on the ground. This is a solid body placing on the ground. Okay, and you are forcing this body in this way. Okay, you are exerting a force on this body in this way, keeping this body fixed on the other side of this body, on the opposite side of the force. Okay, so one thing you should remember, that the body should be fixed on the opposite side, then you are forcing the body on that side. Okay, so this is the side on which you are taking the force on the body, and this is the fixed side. Then what may be possible with this body? The body may get stretched, this body may get compressed on the account of this force. Okay, and if you are applying some force on this body in this way, you are stretching this body on the 2 opposite direction, in the 2 opposite direction, then then another condition maybe that is the body will stretch in the direction of forces. So the forces which you are exerting on the body, which are forming the body, like stretching or compression, this is simple known as deforming force. If you are applying a force on a body and body gets changed into its shape and size, then the force you are exerting is simply known as deforming force, because this force is just deforming the shape and size of the body. Okay, just take a simple example of the real life. If you take a rubber band, okay, and let's say this marker is a rubber band, okay, this is a rubber band, and you are stretching the rubber band in this way. You are exerting force on the one end of this rubber band in this direction, and the other force by the another hand in that direction. Then what will be possible with this rubber band? This rubber band will stretch in this direction as well as in this direction. Now what happened actually? The original shape of this rubber band gets deformed. It has increased its length in the direction of forces. Now it is simply known as deformed body, because it is not like its actual or real or its initial shape and size. Body gets deformed into its shape and size. So these are the two forces which are responsible to create a deformation in the body, is simple known as deforming force. This is simple known as deforming force. And what are the effects which are responsible or which may happen on applying deforming force? The body may get its shape changed, shape may changed, its size may change, and both may change together. So if you are applying deforming force on a body, the body's shape and size may get deformed. Okay, so such type of force is simple known as deforming force. And if I say in the real world, then all the type of forces are deforming force, because they have some outcome on the body. If you are applying some force on the body, body will experience that force, and body will take that force and change its shape and size. So all the forces are simply work as deforming force. Okay, so now what you have to do, you have to apply the deforming force on a body, and then you have to check what is actually happening with the body. Okay, if you are exerting a force on the body and body is deformed into shape and size, okay, then the body is called as deformed body, and the force you are applying is known as deforming force. Okay, the important thing is that what you have to check after removal the deforming force. You have to check the position or states of a body on which you are applying deforming force after removing the force. Let's say you are stretching a rubber band and you release the rubber band. What will happen? The rubber band will snap back into its initial position or its actual position. Okay, so what is actually happening? If you are removing the deforming force, then the body regains its original shape and size. If all the type of bodies on which you are applying the deforming force, after removing the force, they regain its original shape and size, they are simply known as one type of bodies, which are simply known as elastic bodies. Okay, I am repeating the sentence. When we apply deforming force on a body, the body gets changed into shape and size. Okay, and when you remove the deforming force, if the body regain its original shape and size, then that type of body is simply known as elastic body. And this behavior and this characteristic what the body has, which tends to do the body to take into its original position, is simply known as elasticity. And then elasticity can also be defined as, elasticity is the phenomena of the bodies in which if you remove the deforming force applying on the body, then body regain its original shape and size. Done. So this is the first type of the bodies in the universe, which are solid in the states. Okay. If we talk about plastic body, then there is some particular difference between the elastic and plastic body. What is the difference? Now again, you have to check the behavior of the body after removing the deforming force. If body regains its original shape and size after removing the force, then body is known as elastic. And if body do not regain its original shape and size completely, then this is simply known as plastic body. If body do not regain its original shape and size, then this is known as plastic. And what you have to do? You have to apply some deforming force on the body. Body will get changed into shape and size, correct? And you have to remove that deforming force on the body. Now body, if body do not take its original shape and size, then the body is simply known as plastic body. If you take the example of chewing gum, if you stretch the chewing gum into a particular direction and release the chewing gum, then what is happened? The chewing gum do not take its original shape and size. It is permanently deformed after removing the deforming force. That's why the chewing gum is categorized into the plastic bodies. And this property, what the body have, is simple known as plasticity. Okay. If you check sharply to the elastic body as well as plastic body, then you can categorize the plastic body into some different categories also. And what is the different category? Elastic bodies are also of two types. One is perfectly elastic body, and another is simple elastic body. In elastic body or simple elastic body, I am taking it as simple elastic body. Simple elastic bodies, and one is perfectly elastic body, and there is simple elastic body. What is meant by perfectly elastic body? Here there is a bird which is perfect. Okay. So if after removing the deforming force on a body, it regains its original shape and size completely and suddenly. Okay. If this is the elastic body. Okay. I have applied deforming force in these two particular directions. Okay. Then what is happened? Its length is increased in this direction and along in this direction also. And if I remove the force on this body, then what should happen? The body regain its original shape and size completely as this is. This should also be as this is. Okay. So if the length is, let's say this is a 2.5 centimeter, and when you apply deforming force on the body, it stretches up to, let's say this is 4 centimeter, and you have removed the deforming force from the both sides of the body. Then if body regains its original shape and size completely and suddenly, what is the mean by completely? It regains its length 2.5 centimeter and suddenly, this should be sudden process. Okay. Then such type of body and the shape is not changed. If this is a rectangular shape, this is also completely rectangular shape as this is. And this process should happen suddenly after removing the force. If the body suddenly regains its original shape and size completely, then this is known as perfectly elastic body. So here you have to mind two words. One is completely, I am taking it as complete, and second is suddenly. If the changes are taking the complete and suddenly suitable categories, then this is simple known as perfectly body. Okay. And if this is a body, again I am taking the same example. You have applied some force on both sides, body gets reformed, it has increased some length and its shape is changed, and you have removed the deforming force. Now what is happening? The body is regaining its original shape and size, but not completely. Let's say again, the initial length of the body is 2.5 centimeter. Okay, and this is a rectangular shape. You have applied deforming force. It is increased into its length. Let's say again 4 centimeter. You have removed the deforming form from along both the two directions, and body is regained into its original shape and size. Let's say, but not completely. Let's say it again occupied its 4.6 to 4.6 centimeter. The original length is 2.5 centimeter. Body is stretched, and you have to remove the force. You have removed the force, deforming force, and body regained its original shape and size, but not completely. Complete change, complete shape will be 2.5 centimeter, but it is 2.6 centimeter now. Then there is a permanent set of 0.1 centimeter. If this is happening with the body, then this is categorized as simple elastic body, and this is not happening with the body, then that is simple or perfectly body. And you know very well, in the universe nothing is perfectly characteristic of a body. Everything has some negativity, everything has some variation from the ideal value. So this is a just concept, this is ideal concept that a body should have complete and suddenly regaination to get its initial or original shape and size. So such type of body is simple known as perfectly and simple elastic body. You can take example perfectly elastic body like rubber band, okay, and elephant teeth. Elephant teeth is also example of perfectly elastic body. And if you take the spring, if you take a spring of some material like metal material, then that can also be categorized in the perfectly elastic body, because when you stretch a spring and you remove the force, spring snap back into its original shape and size, so that maybe go into the perfectly elastic body. Okay, and simple elastic bodies are, you have to keep difference between a simple elastic body and perfectly elastic body when you come across to the real life phenomena. Okay, now if I talk about plastic body, then this is very simple. If you take a piece of mud, then you have applied some force on the mud or floor, then what happened with the mud piece? That is completely stretched. Or if you take example of smash floor, gutha hua aata, mala hua aata, then what happened with that type of particular material? If you apply some force in this way, then gutha hua aata, smash floor completely set a deformation. If there is a ball of smash floor, this is a complete ball, and you have applied some force on from all the directions, all the possible directions, then what happened? Its shape will be like this. And if you remove the forces, it will not regain to its original spherical shape. So this is plastic body example. And I have taken also a chewing gum example, which can be there into the plastic substance or plastic categories of the substances. Okay, so these are the plastic bodies. Again, plastic body can be perfectly plastic or simple plastic. Again, perfectly plastic means that if body do not regain its original shape and size completely, it has completely or permanently set. If you have applied deforming force, it is permanently deformed for all the time, for every time, then that type of body is known as completely or perfectly plastic body. Okay, so this is what we have, plastic body. Okay, now if we connect these all the bodies according to physical rules, then the first rule given by the scientist Robert Hooke in approximately in beginning of 17th century. I think this is the year of 1607, I think. So I am taking the beginning of 17th century. This rule is also known as the initial rules of physics, 17th century. Okay, Robert Hooke. This is one of the first law of physical science. And what is the rule? Let's say there is a elastic wire, and this is a rigid support on which a wire is tight and it is hanging. Okay, now and its initial length is L. You have applied some load at the other end of this body. Let's say the mass which is loaded on this wire is M, then its weight force will be mg. What will happen with this wire? Its length will increase in the direction of deforming force. So let's say this is the initial length. After loading some force, after loading some weight, its length will increase. Let's say the increased length is this, and the loaded weight is mg or w. Now this what is this? This is the increased length. Let's say this is delta L. If this is a 5 centimeter, let's say this is 0.2 centimeter, and 0.2 centimeter is the deformed or increased length of this wire, elastic wire. Robert Hooke said that if you increase this load on the body, then this increase of length of the body will be greater. Well, in the simple words, if you apply some more weight, if you add some more weight at this end, then what will happen? This wire will stretch more, its length will increase more. Okay, so the force applied, this force applied is proportional to what? The force applied is proportional to what? Increased length. Okay, so this is increased length, and which is simply known as extension. So force is proportional to extension. This is a rule given by the Robert Hooke. Okay, there is another rule which is simply very known as Young's modulus or Young law, which is a modification of the Hooke's law. Okay, and what is that? That is simple relation between stress and strain. And what are the stress and strain? Let's take a look on the simple words of elastic behavior of the substances. So first is stress. So what is the meant by stress? Okay, so stress is nothing but a particular type of force. I am taking the example of a wire. If you zoom out the wire, then that is like this. Okay, if you have applied some weight on this wire, then what will happen? Its length will increase in the direction of weight. Okay, if you sharp look at the area at which the load is tied, then that will be circular. Its cross section will be circular like this marker. If you have applied some load at this end of this marker, then this is circular area. Okay, in physics we compare the one property of the substance to the another. If the length of a wire is very greater in the comparison of its width, then we say there is a negligible width, and we just neglect the width or diameter or radius or area of the wire in the comparison of its length. Okay, but there is some material which is used to create, which is used to manufacture this wire, so we cannot go through that way. Okay, we are here taking the area in the consideration also. Okay, so this is the weight, and weight is nothing but a force. Okay, what is exactly the Newton's third law? If you applied some force in one direction, then there will be a force in the opposite direction which has the equal magnitude as the another force. Okay, so this is the force F1 along downward, then there will be a reverse force having the same magnitude as you are applying. Okay, so it is what it is. This complete force which is in the opposite direction of the loaded weight is exerting internally on the area of the wire. And on what area? That area which is just connected to the load. So this is the force which is exerting the opposite direction of the load applied internally. And this is some area of the wire. So the force, this is the force F which is exerting on the internal area of the wire along its length internally. So this is the force applying on a particular area. Whenever a force applied on a particular area, which is simply known as pressure, but here we will not say it as pressure. Okay, so this is the particular type of force exerting on the area. If I take this area as unit means there is a 1 centimeter square area or 1 meter square area for a long wire and heavy wire, then we say the area is unit. Then the force applied on a particular area, which is simply known as pressure, but here we say that as stress. So stress is nothing but the internal force exerting on a body, the internal force exerting on the body having area as a unit. Okay, or this also can be defined as stress is equals to the internal force exerting on unit area of the body. Okay, so this is internal force, not simple outward force. Okay, so stress is just related to internal force applying on a body, and which is just simple equals to the weight applied. Okay, so whatever the value of weight, that will equal to this force. Okay, so in the consideration, if numerically if you want to fit the value of F, then you have to take the weight applied on the body, because numerically the action equals to reaction according to Newton's third law. Okay, so this is what we have stress. Now this particular type of stress has a unit as that of pressure. So this is the force measured in Newton or kilogram meter per second square, and this is area which is measured in the meter square. So the unit of stress will be Newton per meter square. If I talk about the dimension of the stress, then that will be same as that of the pressure dimension. So this is the force, that is mLT minus 2. This is mLT minus 2. Okay, and divided by area. Area is nothing but length and breadth. This is L square or L2. One power will be cancelled out of the dimension of L. Remain power will be mL minus 1, and this is T minus 2. Okay, so this is the dimensional formula for the stress, and which is nothing but as that of the pressure. That's why the unit of pressure is also as that of the stress. So stress unit is same as that of the pressure. So pressure is measured in the Newton per meter square, so stress will also measured in the Newton per meter square. Pressure is measured into Pascal, then stress is also measured into the Pascal. All the unit of the pressure will be applied on the stress as well. Okay, now there are the different kinds of stress. You can go through them. So let's one by one define the different kinds of stress. One type of stress is tensile stress. Tensile stress, okay, and the type of stress is compressional stress. Compressional stress. And another type of the stress is that is, let's say, normal stress or hydrostatic stress. Okay, hydrostatic stress, and which is simply known as normal stress also. Okay, and another stress is shear stress or tangential stress. Tangential stress. Let's understand one by one these four stresses. Okay, so tensile stress, here is the word tension. This word has come from the tension, and tension occurs in a metallic wire when it is stretched. If you have a wire and you have stretched that wire tightly, then there is a tension force in the wire. Okay, that will equal to the complete force applying on the body. So tensile stress will be when you will stretch the wire. Let's say these are the supports and one end of a wire is tied with this support rigidly, and you are applying the force on this wire in this way along the x-axis. Then what will happen? The wire will stretch in the x-axis and there will be a tension force in the wire in the opposite direction of the applying force. So whatever the force you are applying on the body will generate a stress, okay, which will belong to the what? Tension force of the wire, and that type of stress will be known as tensile stress. So tensile stress is nothing but the stress generated in a stretched wire along to the tension force of the wire. So this is what we have, tensile stress. Okay, next is compressive stress. Just reverse the process. If you are having a metallic rod, okay, and you are compressing the rod from both the sides, or if you are fixing the one side of the metallic rod and you are applying the force on the body in this way, okay, then what will happen? The length of this metallic rod will be compressed on the account of this applying force. In that particular condition, the stress will be in this way because the action is along negative x-axis, so reaction will be along positive x-axis, and whatever the stress by which the body will exerting the same force as that of F is simply known as compressive stress. So compressive stress takes place in a body when it is compressed by a external force. Okay, this is done. Next is hydrostatic stress or normal stress. Hydrostatic word comes from hydro, means water, in static. What is exactly mean by hydrostatic stress? Take a balloon into the water, inside the water, what will happen? Water will exert the force onto the over the surface of the balloon from all the possible sides. Okay, if this is the balloon and you have taken this balloon into the water, inside the water, what will happen? According to Pascal law, water will apply force on the balloon from all the possible directions, okay, and the direction of the applying force will be just perpendicular to the surface of the balloon. That's why this type of, okay, this is the applying force exerting by the water. Now the reverse force which will be applied by the what? Material of this balloon in the opposite direction of the applied force, which is known as hydrostatic stress or normal stress. Water is exerting normal force or normal pressure onto the surface of what? Balloon. Then the reverse force internally reverse force will be also in the reverse direction and which is perpendicular to the surface of this balloon, which is simply known as hydrostatic stress or normal stress. So normal stress comes into the play when a force is applying on a body having some volume perpendicularly. Okay, so if you are applying perpendicularly some pressure over the surface of a volumetric body which has some volume, then the stress which has come into the play is simply known as hydrostatic or normal stress. Okay, last one is tangential stress. Here The word tangential means the tangent. Tangent means a line which touches the plane of a body. Okay. So let's say this is the stool having 4 legs and it is placing on the ground. This is a stool, upper surface. This is the table or board of the stool. Now what you are doing, you are applying a force on this board by taking your hand over the surface of the board. Okay, so you have put your hand over the surface of the board like this, and you are applying force on the surface of the board in this way. According to, you are applying tangential force because you are touching the surface and applying some force. Okay, what will happen with the board? Board may displace in the direction of applying force. Okay, so my hand is just touching, to the surface of the board, and the force by which this board is displacing forward is simply known as tangential stress. Okay, so tangential stress is nothing but when we apply the force on a body touching the surface of the body, then that will be a tangential stress. Okay, the stress comes into the place simply known as a tangential stress. Okay, so these are the 4 types of stress what we have considered up till now. Now for particular type of stress there is a deformation which is simply known as strain. So the another quantity, physical quantity, is strain. What is exactly meaning by strain? Strain is nothing but when you are applying deforming force, then a one property, length, area or volume may increase or decrease. Okay, so whatever the change into the property of a body, let's say you are having a long wire, okay, and you have applied some stress on a force on the body on this wire, and its length is increased up to delta. This is initial length. Then this is what? This is increased. This is a change in the length of the wire. And what is this? This is the original length of the wire. Then the ratio of change in the length and what? Original length is known as simple strain. Okay, if you have a body having some area of cross section, let's say A, you are applying forces on all 4 directions. What may happen? Its area may increase. Then let's say its area is increased up to this. Let's say the change in area is delta A and original area was A. Then the strain in area, which is delta A over A, change in area over original area. Okay, so whatever the physical quantity is changing, change physical quantity divided by original physical quantity simple gives you the strain of that physical quantity. Okay, so if I length is strain, then that will be the change in length divided by original length. If I take the aerial strain, or which is simply known as superficial strain, then that will be equals to the ratio of change into the area to the original area. If I take the example of volumetric body, what I mean by volumetric body, the body possesses some volume. Then whatever the change in the volume, divide that change in the volume by the original volume, that will give me the volumetric strain. Okay, so thus there are 3 types of strains. One is longitudinal strain, another is volumetric strain, and another is shearing strain or shear strain. Let's define all the three strains one by one. Longitudinal strain is nothing but change in the length divided by original length. Okay, you have to take example of a long wire. You have applied some force, its length gets increase up to delta L or decrease up to delta L. Okay, the length may decrease if you apply the force in the positive direction in this way, then the length may decrease. So whatever the change in the length, whether it is increased length, whether it is decreased length, you have to put that change in the numerator, okay, and divide that into the complete or original value of the length. So the change in the length divided by original length, this will, I am repeating, this can be increased length, positive length, and this can be decreased length as well, okay, negative length. Okay, volumetric strength, what I mean by volumetric strength, let's say there is a body having some volume, this is a 3D body like a cube or cuboid, and you have applied normal stress to a body. What I mean by normal stress to the body, you have applied some pressure on the body from the all directions. Then what will happen? The body will compressed, okay, or you are stretching the body from all the possible directions. What will happen? Its volume will increase. Okay, so whatever the change in the volume, divide that change in the volume by the original volume, that will give you the volumetric strain. Okay, and what is the third type of strain, which is shear strain? This is just different than the other two strain. Let's take a sharp look on the shear strain. Okay, so shear strain. Shear strain. Shear strain is defined for such type of bodies which when you apply deforming force, then its shape changed but size doesn't change. Such type of body undergoes to the shearing strain. I am repeating that the bodies on which you are applying deforming force are not changing into their size, the volume is fixed, but its shape is changed. For example, let's say there is a cube here. This is the front view of the cube, okay, and you applied a tangential stress on the upper surface of the cube. Then what are the possibilities which may happen with this cube? Its upper face may displaced into the direction of tangential stress. Okay, so let's say its upper face is displaced in the direction of tangential stress, and now it is here. This is the original position of the cube, and this is the final position of the cube. Okay, this happened with the whole volume of the cube. Okay, if I take consideration of this cube, let's say this is the cube, okay, and you have applied tangential stress on the upper face of this cube, then it's this face, this complete cube will go into this change like this. Okay, let's say this face is here, and this face is here, and this complete face is here, and this complete face is also here. So this will be a change. Okay, so this blue portion is deformed picture of this cube when you have applied some normal force, tangential stress over the one surface of this cube. Okay, now what is actually happened? Actually, its volume, if just imagine a condition that this cube is filled with water. Okay, this volumetric cube is filled with water. You have applied some normal tangential stress. Then what will happen? Water will be inside the cube, whatever the shape of the cube. Okay, so but its size is not changed. Okay, because it's okay, sorry, the shape of this cube is changed, it is deformed. Okay, this angle was 90 degree, now this angle is not 90 degree, it is obtuse angle. This is obtuse angle. So its shape is changed, but size is not changed, because its size is just is as it was. Okay, so such type of strain which is generated is simply known as shearing strain. So you can look here, this is the one edge of the cube which is displaced up to here, and this can be regarded as the angular displacement. Okay, so this is the angular displacement got by this edge of the cube. Okay, simply this is the bottom plate, let's say this is plate 2, and this is the upper plate or top plate, let's say this is plate 1. Okay, and this is the relative displacement of plate 1, upper plate 1, with respect to plate 2. This plate is fixed, this plate is variable, it can go change as you are applying the force. So if I look here, this is a right angle triangle here, the just front side of the angle is simple as perpendicular, this is base and this is hypotenuse. I have to find this change, the relative change of plate first with respect to plate 2. So this is the perpendicular, and what I have the width of the two plates, between the two plates, the length of the two plates. Okay, so the perpendicular base is related to the cot theta or tan theta. So I am taking it as tan theta. What is tan theta? Relative displacement perpendicular over base. So let's say this relative displacement, whatever it is, I am writing it as relative displacement of plate first with respect to plate 2. First plate relative displacement with respect to plate second, divide by what? This is the perpendicular distance between the two plates. This is a perpendicular distance. Perpendicular distance between plates 1 and 2. This gives me the complete deformation got by this cubical body. Okay, for if this angle is very small, then you can go through tan theta as approximately theta. Sometimes this type of strain or this type of change is simple known as theta. Okay, and such type of strain is simple known as shear strain. So shear strain is nothing but tan theta, which is numerically equal to the relative displacement of the plate 1, upper plate, with respect to second plate, and divide by what? The perpendicular distance between the plate 1 and plate 2. This is the shear strains what we can define. Okay. Now let's discuss the very important rule of elasticity, which is simple known as the Young modulus of elasticities. Okay, so let's take the modulus or modulus of elasticity. Okay, there is a one thing also so to mention here. You have to apply deforming force on the elastic bodies under a limit. You know very well, if you apply deforming force on elastic body beyond a limit of the elastic body, then this will deform permanently, whether it is elastic or plastic. If you have a perfectly elastic body, you are applying deforming force up to a certain limit, which is simple elastic limit, then the body will regain its original shape and size. But if you cross this particular limit, let's say the maximum force which can bear by a particular rubber band is 5 Newton. 5 Newton force, according to 5 Newton force, if you apply 5 Newton force on a wire, it can withstand with that. If you exceed the applied force beyond the 5 Newton, then what will happen? Body will not regain it into its original shape and size. Okay, body will behave like a plastic body. So there is an elastic limit for a particular type of elastic bodies. Okay, you have to perform all the experiments, all the phenomena with the elastic bodies under that elastic limit. Okay, so elastic limit is that maximum deforming force under which the body can regain its original shape and size, and beyond that body doesn't regain its original shape and size completely and suddenly. Okay, so that is the elastic limit. Whatever the rule I am discussing in this video and in the later videos, I am performing all the experiments virtually into the elastic limit. So just remember that particular definition and particular phenomena. So modulus of elasticity, what is the modulus of elasticity? Elasticity modulus, let's take a look on them. If you apply some stress on a body, whatever the type of stress in the body, then body may change into shape and size, and whatever the strain in the body that are connected to with this relation. This was very first given by the scientist Thomas Young in the beginning of 19th century. Hooke's law was from the beginning of 17th century, and this rule has come later after the Robert Hooke, and this rule has come beginning to the 19th century. Okay, so stress is proposed to strain. Whatever the stress you are applying, that will equal to the strain in the body, and it is very general idea. If you increase the stress, then strain will also increase. Okay, so, and you know very well, when you convert the proportionality sign into the equal sign, then you have to mention some constant. So let's say this constant is this, and this is strain. The strain will be multiplier of constant. I am taking the strain here. So this is the relation. Stress over strain is just simple a constant. Okay, this is very well known as Thomas Young rule. Okay, now there are the different kinds of stress and strain as well. So we will define this constant for each type of stress as well as strain. Okay, now if I take example of a wire, then whatever the constant will be there will be known as Young modulus. So I am defining the Young's modulus. Young's modulus of elasticity. It is represented by capital Y. Okay, so take example of a wire. This is a wire having length L. You have applied some force on the wire by adding some weight. Let's say this is the weight mg, due to which its length is increased up to delta L. This may be decreased if you apply the force in the opposite direction. Okay, so this is delta L. So let's say whatever the area of this wire cross section is A. So stress over strain. Okay, stress over strain will be equals to constant, and that will be known as the Young modulus for this particular wire. If you take the example of the body which has some length, then that particular constant which is related to the stress and strain is simply known as by Young modulus. Okay, so stress is nothing but force divided by area, and what is the force you are applying? Mg, weight of the load body. Okay, so stress is nothing but force over area and divided by strain. What is the strain? Change in length divided by original length. So this is delta L over L. This is Y. And what is the value of F? F is nothing but mg. This L will be into multiply of F, mgl. Area will be into multiply of delta L. So this is delta L and this is A. If the area of cross section of wire is circular, then the area of cross section of circle is pi r square. This will be the Young modulus of elasticity for this particular wire. Okay, what is the physical significance of modulus? Actually, by decides how much this wire will stretch or compress. You can easily see here, if bi is greater, then strain will lesser. It means that if bi is greater, then wire will not stretch whatever you are forcing, you are applying the force. It represents the stiffness, hardness, rigidness of a wire. Okay, so all the type of modulus represents the stiffness, rigidness, and what, the hardness of the wire or the particular body. Let's say if you are taking the example of jumper cricket ball and rocky cricket ball, then jumper cricket ball is just a very loose ball. You can compress that ball by applying some normal force. And if you want to compress a rocky cricket ball, the cricket ball having company rocky, then you will have to apply some more force, more pressure to compress that particular ball. So we can say that rocky ball is very hard in the comparison of jumper ball. And here the modulus of rocky ball is greater, is very greater in the comparison of jumper ball. So the modulus of elasticity gives you the information how the body is hard and rigid according to the elasticity. Okay, so then jumper ball has more elasticity, they can be compressed more, and rocky ball has less elasticity, it is inelastic, it shows the inelastic behavior. Okay, so this is the modulus physical significance. So we have defined by. Now second modulus is bulk modulus. Bulk modulus is represented by symbol kappa. This is K-A-P-P-A, kappa, or you can call it as K also. Okay, so I will call it as K. Okay, this modulus is just related to those type of bodies which has some volume. So take example of balloon or ball. So this is a ball having some volume B. Okay, you have apply a normal or hydrostatic force. This is a ball, okay, having some volume B, and you have applied some hydrostatic force or normal force or pressure or stress on the body. Now what will happen? Its volume will decrease. Let's say this is stretched, so this is compressed up to here. This is the original volume or shape, and this is the final shape. Now let's say the volume is V dash. Okay, so this is the change in the volume. This is the initial volume of the body. Now the body is this, and this is the change in the volume. Okay, now what type of stress you are applying? Simple pressure, hydrostatic pressure. Then stress divided by strain equals to what? Modulus. So stress is nothing but P, directly P. And what is the strain? Volumetric strain. Volumetric strain, change in volume delta B divided by initial volume. And this is the modulus for volume body. And here the modulus is K or kappa. Okay, here the volume is decreasing, that's why I can take as negative here also. This V can be written in the multiply of P also. So this is the bulk modulus of the body. So bulk modulus is for those type of bodies which have some volume. Okay, so this is the bulk modulus. Now there is a third modulus which is simply known as modulus of rigidity. This is the third modulus, modulus of rigidity or shear modulus. Shear modulus, which is simply represented by eta. This is for those type of bodies which changes into their shape, not size, like a cube we have discussed earlier. Okay, so shear modulus is just you are applying, this is the cube front view, and you have applied a tangential stress on the body in this particular portion. This is the tangential stress, this is the area you are applying some force F, this is the particular area A, so this becomes also pressure. Okay, so F over A, and this is a theta. shear strain. So the stress divided by strain, this is F over tan theta or theta, will give me what? Shear modulus eta. For the small angles, this is simple written as theta. So eta equals to force, sorry, this is force over area, this is pressure, okay. So pressure over theta gives me the shear modulus, okay. So this type of bodies undergoes to the shear modulus, okay. Now if I talk about units and dimension of the modulus, then the simple rule is stress over strain equals to modulus of elasticity. So any type of modulus, whether it is y, whether it is k, whether it is eta, that will have the dimensions and unit as that of stress over strain, okay. And stress is simple pressure, and stress, what is the stress? The change in the physical quantity divided by that particular physical quantity. Length, change in length divided by length, length unit is cancelled by length unit. And if I talk about the volumetric strength, then delta V over V, the meter cube over meter cube is cancelled, okay. For the young model tangential strain, about tensile strain, what is happened? Strain, change in length divided by initial length, so meter divided by meter. So there is no unit and dimension for strain. Whatever the unit and dimension of stress, that will equals to this unit of modulus. So by and k and eta are measured in Pascal or Newton per meter square. And dimension will be same as that of the pressure, ml minus 1, T minus 2. These are the MKSC unit or SI unit, okay. So there is one constant is also there related to the elastic bodies, and that is Poisson ratio. So what about Poisson's ratio? The Poisson is the name of a scientist, okay. So this is the Poisson ratio given by that, and the abbreviation or symbol of the Poisson ratio is sigma. If I take example of a metallic rod or any type of material rod like this, okay, then it has some length and it has some diameter, okay. So it has some diameter, let's say this is D, okay. Now what you have done, you have applied some force on this body, on this metallic rod mg. What will happen? Its length will increase, okay, and just point out here, it will compressed toward its what? Center axis, okay. So this is the axis. Then what will happen? The wire will be thinner. Then let's say the wire will become like this. The blue marks are showing the final position of this what? Metallic rod, and this is the initial position. I am taking it as dotted. So black diagram of this metallic rod showing its initial position, having diameter D and length L. When you applied some weight mg on this metallic rod, then its diameter is changed. Let's say that initial diameter is D1 and now diameter is D2, then the change in the diameter is delta D, okay. And let's say the length which is increased is delta L. Now this happened with all the type of wires which are stressed on account having some load to their at ends, okay. So both two conditions are happened. One is its length is increased, okay, and its diameter is decreased, its area decreased, because when you stress some wire, then its length is increased and it becomes thinner, it becomes thin in the comparison of its initial height. This is just general idea you can go through. Okay, so here there are the two type of strains which are in this play. So one is what? One is tangential strain or tangential strain. Sorry, tensile strain. Okay, and which is equals to what? Delta L over L. This can also be written as longitudinal strain. Okay, I am taking it a longitudinal strain. Okay, so this is delta L over L, changing the length divided by original length. Let's this equation number 1. And there is a change in diameter also, and that diameter is used for the area, and area is just simple known as the lateral property of a body. So that type of particular strain is simple known as lateral strain. Lateral strain. And lateral strain is what? Change in diameter divided by original diameter. And diameter is decreased, so I have taken it as negative. So equation 1 is longitudinal strain, equation 2 is lateral strain. The ratio of these two strain is simple known as Poisson ratio. So, and what is the ratio? The ratio of lateral strain to the longitudinal strain. You have to mind it. Lateral strain divided by longitudinal strain will give you Poisson ratio, not this divided by that. So Poisson ratio equals to what? Lateral strain divided by longitudinal strain. Okay, so lateral strain is what? This is delta D over D, and divided by what? Longitudinal strain, this is delta L over L, and it is going to equal sigma. This also can be written as minus delta D over delta L and what? L over capital D. This is what we have the Poisson ratio. Okay, so up till now we have defined the Young modulus Y, the bulk modulus K, and the shear modulus eta or modulus of rigidity eta, and another elastic constant which is known as sigma. Okay, so I think this is enough to know about the mechanical property of solid, basic concepts. So in this video we have defined the different types of moduli, and in the second video and the second part of the mechanical property of solid lecture we will derive the relation among yk, eta and sigma. Okay.